So this is a distortion pedal. So we can distort the guitar if we want, and we can make it sound different. Yeah, so that's like, turning the knobs on the pedal kind of. And then part of the way that I've designed this plugin is that you can actually look at the circuit and fiddle around with some of the component values if you want to. So for example, let's see what happens if we change the capacitor 2 here. Maybe I'll make it louder first. Maybe we'll make it like 1 millifarad or like 1 nanofarad or something. So it just kind of makes it quieter or louder. But yeah, different circuit components will do different things depending on the settings of the knobs and the values that you choose and so on. So yeah, this is generally what I do. Like when I go to work, I try to make software like this. Sure. Sure, yeah. Well, I don't have the one that I had in the screenshot there, but I've got my own one here. Although the way that I did it for this plugin is I've got half of the circuit here, which is like the distortion part of the circuit, and then there's also a tone circuit which I have here. The Centaur. And then yeah, this one has a circuit too, but it's really big. So that's the Centaur circuit, or everything except for the tone stage in the Centaur circuit. So again, we could change things if we want. Everything really small, I guess. Sure. Well, yeah, that's a very good question. So the question was, why not just build that circuit instead of spending the $10,000 to buy one? It's a complicated answer. Part of the reason is that musicians are, they sometimes get obsessed with like the mystique behind a certain piece of gear more so than like the physics of how it works. So there's kind of two things that are special about the Centaur, or like the original Centaur. So one is that the circuit design was pretty novel for the time. There's a lot of things about it that weren't really done before, but that's something that like there's a lot of newer pedals that either copy that pedal design or kind of have their own take on it that, in my opinion, you can get the same sound from. There's also these very specific diodes that were used in the original circuit build that they were from some like tiny factory in Russia. Eventually that factory closed. The guy couldn't get the right diodes anymore, and I think that's probably why he stopped making the pedal. Apparently nothing else sounds quite like those diodes. Maybe it's real, maybe it's snake oil, I don't know. But yeah, once like people get it in their heads, they're like, oh, if I get this pedal, it'll make me sound great because Noel Gallagher, Eddie Van Halen used this pedal or something. Then yeah, there's a lot of kind of weird. There's a lot of weird things that happen in pricing for audio gear. Like there's a strange thing that happened a couple months ago. There's a guy on YouTube who makes videos about guitar pedals, and he did one where he got this pedal called the Bad Monkey, which was from like 2004 or something. That was not very popular when it came out. And it's like the point of the video from his perspective was to show how like you can get good guitar tones even with like old and cheap pedals. And so he did a thing where he like compared the sound of that pedal in different settings to like other famous pedals, including the Centaur. And what happened was at the time you could get the pedal for like $50, and like 2 weeks after the video came out, it was like 600 or something. And he's like, that's not the point. Like the point is you can get this kind of tone for pretty cheap if you look and you learn to get your settings right. People didn't take it that way, so I don't know. It's a weird world. Definitely. Well, if the intro is missing, I think it's probably okay. But yeah, so that's basically what I work on, and so now I can talk about kind of how it works. So the first thing is kind of just thinking about audio programming in general and the constraints that we're working with when we're trying to program for this environment. So much like programming for graphics, you have kind of a data rate. So with graphics, you have a frame rate of usually like 32 or 60 or 20 times per second. With audio, it's 48,000. They call it samples. So that's like one block of, or one segment of time in your audio stream is a sample. So you get 48,000 of those in a second. So it's much faster than like the graphics world, but unlike with graphics, we have to put thousands of pixels on the screen. We typically only have 2 samples at a time, one for the left channel, one for the right channel. So it's a very different problem from that perspective. So typically what happens is your audio driver or some system below you will chunk those samples into a buffer, and maybe a common buffer size is like 500 samples or so. Maybe it's as low as 50 or maybe as high as 5,000 or so, somewhere in that range. And so the system below you, whether that's your audio driver on your computer or the plugin host that you're living inside of, will call into whatever function you're using to process audio. We call it the audio callback. Once every approximately 10 milliseconds, maybe it's a little shorter, a little bit longer. And that's what we call the real-time deadline. And what that means is that if you miss the deadline, you'll get a glitch. So usually it sounds like a little bzz, or something worse sometimes. The technical name for that is a buffer underrun. And generally in audio software, if you have buffer underruns, that means your software is not really usable. Because if you're on stage or you're in a recording studio, you don't want something like that ruining your performance. Yeah, musicians really hate that. And kind of the problem, or the problem on top of the problem, is that these days a lot of musicians want to be able to use hundreds of plugins at a time. So your 10 milliseconds is really maybe only like half a second. You're sharing resources with all of these other effects that are part of effects and synthesizers that are part of the musician's workflow. And so what that means for me is that small optimizations really matter, because if my plugin sounds better than my competitors, but my competitors is much more efficient, then a lot of people are probably going to go with my competitor because they can use more other effects as part of their recording session or whatever, instead of just using one of mine. So that's something that people think about a lot when they're making music these days. Cool. Any questions about that stuff? All right. So now we'll kind of switch gears and talk about circuits a little bit. Folks here, somewhat, people know what voltage is or current and things like that. Yeah, it's kind of where we'll be starting from, and specifically we'll be starting with this circuit. This is just your standard RC low pass filter. So you've got a voltage source, which in signal processing terms, we would say that's our input signal, is the level of that voltage source at any given time. We've got a resistor and a capacitor, and then we'll say that the output signal is the voltage across the capacitor at any given time. And the idea here, do folks know what this circuit does? Mostly, okay, cool. So if you've studied circuits before, you might know a little bit about nodal analysis, and that's a perfectly valid way to create a model of this circuit. So basically what you would do is do a Laplace transform. I'll kind of wave through all the math here. But you would come up with some transfer function that describes the behavior of the circuit in continuous time. That's basically the ratio of the output to the input voltage. And then what you would want to do is you would want to discretize that continuous time transfer function. And we have a thing called the bilinear transform, which is one way of doing that. There's a few others that are also popular, but you end up with a digital transfer function in what we call the Z domain, or Z domain if you're Canadian. And then that's something that you can actually implement in code. So here we have what we call a signal flow diagram that basically shows the operations that are involved in implementing that filter. So for example, B0 here is a multiplication, the plus is an addition, and then the Z minus 1 thing there is a 1 sample delay. So you would have some memory in your code, basically like a float or a double or whatever data type you're using, and you would store the value there, and you'd wait a sample, and then you would replace it with something else and use the value that you had previously. So yeah, that's a basic way of modeling this circuit, and we're done. That's the whole talk. But really, it's not, because there's problems with doing things that way. The main issue is that it's not a very modular way of modeling the circuit. And what I mean by that is that every time you change a component value, you have to redo the discretization step. If I had spelled that right, that's what you would do. And so the problem that you have is that, let's say you want to be able to change the cutoff frequency of your low pass filter. Well, then every time you move your knob or whatever you're using to control that, you have to redo the discretization step. Now you have a time varying system that's got lots of problems in general, but the worst issue is that every time you change your circuit, so if you swap out the capacitor for an inductor, or you add more components to the circuit or whatever, you need to rederive everything from scratch, basically. And people like me, we're lazy, we don't like doing that. And so we look for better ways. And the first thing you might try to do is to just take that way of doing things and make it modular by just discretizing each component on its own, and then saying, okay, this is in series with that, or this is parallel with that, or whatever. And that doesn't work. So this is a slide that I borrowed from my friend Kurt, where he tries to go through to do that. You discretize the voltage source, the resistor, the capacitor. Everything seems fine until you glue them together, and then you end up with this thing called a delay loop here, which basically means that this signal flow is non-computable, because in order to get the output, you need to already know the output to compute the output, and it's a endless loop there. There are ways of resolving delay-free loops in circuit simulation, but for a really simple circuit like this, we don't want to have to get into that kind of thing usually. So we'll basically say that this is the kind of fundamental problem in circuit simulation in general, which is that you want to be able to do things in kind of an automated way, but you don't want to have any delay-free loops. Figure out ways to resolve the delay-free loops when you do. And there's a number of ways that people have come up with to do that. The problem with most of them, from the perspective of giving a talk about C++, is that they're really hard to write code for in a way that really makes sense. So what I've done before is write like a Python script or something that generates my C++ code. But to me, that's not that fun to talk about. One of the things that I really like about wave digital filters is that you can just write everything in C++ and just lay out your circuit as a bunch of C++ variables and objects and so on, and then you have a working circuit simulation. And so that's what I'm hoping to get to as we go through here. So when we're doing wave digital filters, we kind of have to start from the beginning and basically say, we don't want to use voltage and current anymore. We want to use these things called wave variables. So in traditional circuit analysis, you have basically a node here and a node there, and some thing that goes between those two nodes. We'll say that thing has an impedance R0. Then you have a current going from one node to the other, and a voltage that is between those two nodes, right? In the wave domain, we say that we have a port, which has this impedance R0, and we have an incident wave going into the port, and a reflected wave coming out of the port. So if you ever looked at like waveguides or things like that, this might look kind of familiar. It's taken from the same idea of how to do things. So when we want to structure, or when we want to create a circuit model, we have to create this tree-like structure where basically you have some root of the tree. Everyone puts the root at the top. Wouldn't have been my choice, but I'll stick with it, I guess. And then you have your circuit elements, for example, a resistor as like a leaf of the tree. And then in between, you have these adapters. So for example, if we want to say that these three circuit elements are in series, we can connect them with a series adapter. And so generally the way that I think about it is that the series adapter has one parent node, which is the root, and then two child nodes, which are these R1 and R2 here. So the way that the rules for putting together this tree are that each port has to have these three variables: the incident wave, reflected wave, and port impedance. And then you have some nodes that are leaf nodes, so those have one port, resistor, capacitor, inductor, voltage source, things like that. And then you have adapter nodes, which could have 2 ports, 3 ports, sometimes more. So maybe that's a series adapter, a parallel adapter, or a polarity inverter, something of that sort. And then for the root of the tree, we have special types of nodes that go there, which we call unadaptable. Not going to get into that, what that means right now, but specific unadaptable nodes might be a ideal voltage source or current source, or something nonlinear, diode or switch. And yeah, if you think about what happens when you have a circuit with multiple nonlinear things, that's where things get really hard. But I don't know if we'll get to that today. So going back to our low-pass filter, this is our RC low-pass filter. We have our resistor here, our capacitor there, our series adapter here. Then we have an ideal voltage source. That's the root of the tree. And so the first thing we want to do is we want to set our source values. So this is our input signals, essentially. So we say, whatever our input signal is at this time, we'll set the value of the voltage source to that value. Step 2 is that we propagate all of the reflected waves from the leaf nodes. So R1 has this reflected wave here, C2 has this reflected wave there. We propagate those down until we have some reflected wave going into the root. Something that can be a little confusing is that whether something is incident or reflected kind of depends on which way you look at it. So for the series adapter, this red arrow is a reflected wave, but for the voltage source, it's an incident wave. So then what you do next is you compute whatever you need to do at your root. So basically, you take in your incident wave, figure out what your reflected wave needs to be. And then you can propagate that as an incident wave going into the series adapter, then back down the tree, up or down the tree, depending on how you want to orient it. And then finally, you compute whatever output signals you need. So in this case, we want to know voltage across the capacitor as our output. And that's everything. And you might say, well, that seems way more complicated than nodal analysis we did at the beginning. And you're mostly right, it is complicated. But the advantage is that we can reuse everything that we've done with wave digital filters to model pretty much any other circuit to a point. So for example, we could look at this RC diode clipper. So basically what we've done now is we've added this diode pair in parallel with the capacitor here. And what we're going to do, since we can only have one unadaptable node in our tree, is we're going to combine this voltage source and resistor into one node, which is basically like a non-ideal voltage source that has some volt resistance attached to it. And so this is our new wave digital filter tree. We've got the diodes at the root. We've got our combined resistor and voltage source as the first child element of our adapter, and the capacitor is the second. And now we're using a parallel adapter instead of a series adapter. And everything that we've done up to now can be reused again and again for whatever circuit we want. That's kind of where I'm going to stop with the wave digital filter theory. But if you want to know more about this, there's a bunch of links here. This Vetvice paper from 1986 is kind of the original reference. And I forgot about it, at least in the audio world, for a while until this paper from 2008. And then kind of between 2013 to 2016, this guy named Erlanger came along and really kind of advanced things quite a bit. And then my friend JJ wrote this paper. So basically, he presents a model of this giant tube amplifier that probably no one would have even tried to model maybe 10 years earlier, but he got it sounding really good and fast enough that you can run it in real time. Yeah, it's really impressive. But yeah, so now let's look at some code. And the first time that I tried to implement my own wave digital filters, I looked at it and said, well, that's just an object-oriented system right there. You have basically a base class that has everything we need in it that's common to all of the different wave digital filters. So you've got your three variables, the incident and reflected wave, and then the port impedance. For every wave digital filter element, we need to be able to input an incident wave, take out a reflected wave, and tell it that it needs to recompute its internal impedance. And then we also want to be able to convert between wave variables and voltage and current. So we have a way of doing that, which, yeah, it's not too fancy. But then from there, it's pretty easy to implement our basic circuit elements. So this is a resistor here. We give it some resistance value, which we'll call R, and we can just keep track of that in ohms. The port impedance is just equal to the resistance value, and then we can then do a little math to figure out our incident and reflected, what our incident and reflected waves need to be. And then we have a capacitor, which is a little bit more complicated. So with the capacitor, again, we have a capacitance value, but when we go to compute the port impedance, you might notice that it also depends on this thing called FS, which is the sample rate. So we also need to keep track of the sample rate. And then the capacitor is a stateful element, so we also need to keep track of the state and maybe let people reset the state whenever they want to. So now where it kind of gets more complicated is with the adapters. So with the adapters, we want to know what the children are. So this is essentially a 3-port adapter. It has 2 children and then 1 parent. So we can basically take pointers to the 2 children. And then when we want to update the impedance for the series adapter, that's going to be the sum of the 2 child impedances. And then kind of where things get interesting here is that when we want to get the incident wave from the series adapter, or sorry, input an incident wave into the series adapter, we also can propagate that wave further down the tree to the child nodes. And then similarly with getting the reflected wave, we can get the reflected waves from the children, figure out what our reflected wave is, and then continue passing that on tree. So that's a series adapter. Parallel adapter is very similar. And so with that, we can actually implement a low-pass filter like we had just a second ago. So we'll create a resistor, capacitor, connect them with a series adapter, and then create a voltage source. We have to tell the circuit elements about our sample rate, so we can do that. And then when we want to process a sample, we can go through those 5 steps that I went through minutes ago. We can set the voltage level of the voltage source. We can get the reflected wave from the series adapter, put it into the voltage source, and then get the reflected wave from the voltage source and put it in as an incident wave to the series adapter. And then finally, we can actually look at the voltage across our capacitor. We're done. That's a low pass filter. Yeah, any questions about that before I go on? Oh, sure. That is in the base class. That's the port impedance. Yeah. Yeah, so that's maybe I should have made that a little bit more clear. There's a difference between the port impedance R0 and then the resistance value of the resistor, which is just R. Maybe not the best naming choices on my end. Yeah, so problem with that from a performance standpoint, some of you probably already guessed this, but if we look at the output of our compiler with optimizations and everything turned on, we can actually look at what it's doing here when it tries to run that circuit simulation. And you might notice that there's all these call instructions that show up here, and we can look here at what's making those call instructions happen. Essentially, whenever we make a call through to the WDF base class to get the reflected wave or pass in an incident wave, the compiler doesn't know what type that is. So it has to do it through this call instruction, and yeah, no one's. Yeah, so basically the compiler isn't really able to inline these function calls, and that slows things down. So yeah, whenever we're doing the virtual function call, we have a function pointer, table lookup happening. It's not like horribly slow, but when you're trying to, really micro optimize or just get that little bit of extra speed, it definitely does make a difference. And I'll have some numbers that I can show later on. But basically, for every node, you have one incident call and one reflected call per sample. So that winds up being about 6 virtual function calls just for our simple RC low pass filter. So you imagine as you go to bigger circuits, that becomes much worse. So then you could say, okay, well, let's use templates instead. And what I find interesting about this code is that I haven't figured out how to do anything like this in another language. I tried doing it in Rust. Possible that there's a way, but I couldn't figure it out. So I don't know. Maybe this is something that's unique to C++, but maybe I'm just not good enough at Rust. I don't know. Totally possible. But yeah, I'd be curious if anyone has thoughts on like how you do this kind of thing in other languages. I haven't tried D actually. I should do that. For sure. Yeah. Is it directly like drop-in compatible or does it need some tweaks? For sure. For sure. Yeah. Yeah, I should try D. There are a good number of people who are doing audio programming in D these days, and it seems pretty cool. Yeah. Any questions before we dig into this? All right. Yeah, I'm sure some of you have done this kind of thing where you go between polymorphism and templates before, so this will probably be familiar, but the way I'm doing it here is that I start with a struct of all of the common member variables that I call WDF members. Same things we had before, the port impedance, the incident wave, and the reflected wave. And then when I have my resistor, I just have an instance of that class that I call WDF. And so all of these classes that you're about to see have that same struct, and it's still called WDF in every one of them, just as like a common thing. And then everything else is basically the same. You can set your resistance, and you can get your reflected waves. And yeah, capacitor is about the same too. Where it gets more interesting is with the series adapter. So the biggest change is that now we have those 2 child port types as templated types. And so now we can actually have them be references instead of pointers, which is a nice little benefit. How competence is the same. What's nice here is that when we do incident and reflected, we actually, or the compiler knows at compile time what types those are. So we can inline those function calls and do whatever other optimizations we do. So we got a nice little benefit there. And then we want to probe the voltage and current. We have to do it a little bit differently. Which, yeah, the way I have it set up here is that it's something that happens outside of the classes. So you would just call voltage on your circuit element instead of calling my circuit element dot voltage. Not too much difference, really. And this is our RC low pass filter again. You might notice now that when we're doing our series adapter, we use these decal type things to get the types of R1 and R2. For this example, it's probably faster to use like resistor T instead of decal type R1. But as your circuit gets much bigger and more complicated, the decal types usually end up being the way to go. Someone had told me that you should be able to use, they call it CTAD or something, to not need those template arguments. I tried doing that, and it works if you like create it as a variable somewhere that's like a class member. But if it's a class member, then you need to explicitly give it the template arguments. Setup is the same, and then process sampling is the same. But now, if we look at what the compiler gives us, it's been able to inline all of those call instructions. Simplify this quite a bit. So yeah, I'll show you guys some numbers in a second, but the generated assembly ends up being much more optimal than with the polymorphic implementation. Cool. Yeah. So when thinking about template implementation versus polymorphic implementation, the pros is that it's way faster because the compiler can see through everything and inline everything. So for most circuits, it ends up being somewhere between 2 times and 4 times faster. The cons are that the biggest con for me is that the circuit topology is fixed at compile time. So one of the really neat things about wave digital filters is you can actually design your own circuit at runtime if you want. But if you want to use a template implementation, you can't do that. Use some of that flexibility. It's also a little bit more complicated, and then sometimes I'm trying to teach this kind of thing to people who know their math, know their audio stuff, but aren't really familiar with C++. Seems to kind of scare them a little bit. So there's a way to make that easier for them, but yeah, it's been a challenge for me sometimes when I'm trying to teach this stuff. And so finally, I just wanted to present this little library that I had made. It's all on GitHub, and I made a little reference paper too, if you're curious about it. So it's open source. I think it's the BSD 3 clause license. And it's set up with CMake, or you could use it as like a header-only library. And I set it up so you can use either the template or polymorphic implementations. They're both available. So if you do want to be able to make your own circuit at runtime, you can do that too. There's unit tests and whatnot. And right now I've got most of like the linear circuit elements, so like resistors, capacitors, and so on, and also a bunch of diode models as well. I did an implementation of what's called RType adapters, which I'll talk about in just a second. And I also set it up so that you can use it with different data types. So if you want to process a signal that is like a float or a double, you can do that. Or if you want to process a SIMD data type, you could do that too. So for example, there's a lot of synthesizers that are like 4-voice or 8-voice synthesizers. And so pretty nice because you can just have one instance of the circuit and then process a SIMD block that has 4 floats in it or something at a time. So that's a nice little optimization as well. And then if you want to implement your own circuit elements, or have some diodes that sound just like the ones in the Klon Centaur, you can do that too. So in thinking about performance, here's a few benchmarks that I did, just comparing the template and the polymorphic implementation of my library with a couple others that are out there. So WD models is a library that was written in the Faust programming language. Does anyone here know Faust? Okay, it's very niche to the audio world. But it's a very cool language, and it's also kind of like a compile time fixed thing in Faust. So that's why the numbers are pretty comparable to the template implementation. And then RTWDF is like also a polymorphic type of C++ library. So yeah, those numbers look quite similar as well. I actually figured out a way how to make the FF2 circuit faster in my library than in Faust, but I'm not sure if it's cheating or not, so I haven't included those numbers here yet. Yeah, I don't know. I'll think about it, but I use it in my own code because it's fast. And then, yeah, so I have a few other features that were a little bit more kind of involved on the C++ side. So one of those things is that sometimes you have a bunch of circuit components that you want to change the value of all at once. What happens when you change the value of the circuit component is that it triggers all of the circuit elements further up the tree to recompute their impedances as well. And so if you need to change a bunch of component values and they're all going to propagate their impedances up the tree, you may want to wait until all of those circuit values are updated before you propagate the impedances further up. Because sometimes that can be kind of an expensive operation, which I'll actually show you guys in a second. So you want to be able to postpone those updates. So that's what this little scope for impedance propagation is. So basically you say, hey, these elements, don't update your impedance until this thing goes out of scope. And then once that thing has gone out of scope, all of those other elements can update what they're doing and propagate those updates further up the tree. But yeah, the hardest thing, both from a math and circuit modeling perspective, and also from a C++ perspective, is this thing called an RType adapter. So one of the problems with wave digital filters, as I've presented them up to now, is that everything has to be able to be broken down as either a series connection or parallel connection, and that's not always true. So coming from like a graph theory perspective, they have this thing called an SPQR graph, where S and P are series and parallel. I've been told that Q will never happen in a circuit, so I just don't worry about Q. And then R is a rigid node. And what's different about rigid nodes, so series and parallel adapters are always the same. If I have a series adapter in one circuit and in another circuit, I can just use the same code and it'll work. With a rigid node, depending on the topology of your circuit, it needs to be different for pretty much every circuit. So this is the way that I do an RType adapter in my library. So again, you need to have one upward facing port, then all of the other ports will be like child elements. We have this impedance calculator, which I'll come to in a second. And then all of our child ports can be stored in these other types, which we'll call port types. And we can have a tuple of references to those port types here. So when we initialize the RType adapter, given all of those port types as references and use it from there. When we do calc impedance, we go through this impedance calculator, which I'll get to in a second. And then the fundamental thing that's happening is we have basically a scattering matrix. So we need to do a matrix multiply between all of the incident waves, and that will generate all of the reflected waves for us. So I have an array that stores all the incident waves, an array that stores all the reflected waves, and then the scattering matrix here, which I'll see how to generate that in a second. And so when we call incident, we basically figure out what all of our incident waves are, and then we do the scattering matrix operation. And then when we have reflected called, we just spit out all of those reflected waves that we just computed. Then what's going on with the impedance calculator, that's this other template struct that we have here. And basically what we need to do is get all of the impedances of the child elements, and then we can use that to compute the scattering matrix. And this is kind of hard to figure out. So I have a script in Python that uses the SageMath library, and then I recently did a version of Mathematica as well, so that it uses like a symbolic algorithm to generate the scattering matrix. And this can be kind of expensive to do, so that's probably why I had that defer impedance thing. Why I brought that in. So that's how we set the scattering matrix, and then we also need to figure out the impedance of the upper facing port. Again, some complicated expression. Yeah, so that's RType adapters. In maybe 5 minutes. It's a big topic. I could talk about it for hours, but hours. So yeah, I just wanted to thank a few people who helped me both learning about wave digital filters and who spotted some of my early, let's say, pitfalls in my C++ implementation. As you might have picked up on from my little intro, I didn't really study computer science. I was doing electrical engineering and music and everything, and I kind of had to pick up a lot of things as I went along. But folks like Eyal and Paul got a lot with learning how to do templates and so on. But yeah, I just wanted to say thanks again. I'm happy to do more demos or take questions. Anything audio related or sequence related. What the?
Just brief history out way back when I started college. I was a music major for 2 years, but was interested in what kind of things you were doing. So I went over to electrical engineering, and they the music department looked at me funny when I wanted to take calculus. Then I went to engineering, and why are you taking these, these music classes? So it's great to see. One thing is, it's great to see they finally put these things together. So, Yeah. It's a lot farther along than it was me, but yeah, so it's great to see. But the question I have is about 10 years ago, I started just for fun looking at these audio plugins and everything. And at that time, even then it was really impressive. I saw some of the text boxes and things way back when. Like images of them, like you showed with the one there. And I got to thinking, well, how much more can we do? But now you're 10 years later, I mean, there's even more. I mean, is this a competitive market now, or what's how do like the different companies compete with each other now? Because it seems like they've got everything that you could imagine.
Yeah, so that's kind of a complicated question. No, it's good. So I started making music with computers probably in 2014 or so. And even between 2014 and now, well, I guess that's 10 years, yeah. Yeah, the number of plugins and like the number of companies that are making plugins has exploded, and I'm not sure I totally understand why. And I definitely feel like there's probably too many companies doing it now. Um, but as far as like some of the advancements and like things that people are competing with, there's definitely from like the circuit modeling world, there's definitely an aspect of like doing more accurate models and modeling more complicated gear and trying to, you know, make your models more efficient and so on. And I don't know. To me, that's a little bit like it's a great engineering challenge. It's not such an interesting creative challenge for me. Um, I'm really interested in what's going on, kind of the people who are like, well, okay, there's all of this great analog gear and people are modeling it. It sounds great, sure. But we have, the whole world of digital computing available to us. Like, what can we do with that? And so there's a lot of really interesting things that people are doing with synthesizers, with like spectral wavetables and so on, that are kind of like new synthesis techniques that people hadn't done before. Folks who are doing things with machine learning, where it's like, okay, I can figure out how to like morph my guitar so that it sounds like a trumpet or like a saxophone, or maybe it sounds 50% of each, right? And so there's lots of like really interesting things that people are doing now that at least computationally probably weren't really possible maybe 10 or 15 years ago. But yeah, there's definitely an aspect too of just people who are like, oh, people are making plugins and making money from it, so maybe I'll try doing that too. Maybe they're not really doing anything new or interesting, but I guess they're making money. They sometimes hire me, so like that. Yeah. Questions?
Oh, okay, I'll be that guy. How's AI fit into all this?
Yeah, that's definitely an interesting question, especially maybe of the last 6 months or so, where more and more people are talking about like auto generating music and things like that. There's even a friend of mine was working on an app a little while ago where it was like, oh, you create your own song and then you submit it to their app and it'll change the song so it sounds like Drake was singing it instead of you. Apparently Drake got mad about it or something. I don't know. But yeah, there's definitely like a lot of questions there, especially about like, oh, who owns what? Like if an AI is generating song, or if the AI was trained on your songs, should you own some of the songs that the AI creates and things like that? For me, though, it's kind of a lot simpler. So for me, what I like doing is just making simple things that sound good and that I can, play with my keyboard or my guitar or so on. So like a project I was working on last week was I built a fuzz pedal and kind of modded it to sound the way that I like it. And then I trained a neural network so that it basically can recreate the sound of that pedal when I play my guitar into it. And I think it sounds really good, and it's much more efficient than all of the kind of wave digital filter models that I tried to do for that kind of circuit. The negative is that I can't, like I was doing earlier, I can't like pull up the circuit schematic and modify each component and, have it sound different depending on that. But yeah, I think it's really interesting. The other thing that I've been doing within the world of wave digital filters is like, let's say you have your diodes, most circuit elements, we understand pretty well what they do. But let's say you have some unique diodes like the Clon Centaur or whatever has these special diodes and you want your diodes to sound like those. Well, you can just train a neural network specifically for the diodes part of your wave digital filter and basically have that be a drop-in replacement for your normal diode model. So that way, basically like the way that people think about it is that in circuit modeling, you have what's called a white box model, which would be like a wave digital filter where you need to know each component and where it goes in the circuit and kind of understand it at that level. Or you can have a black box model, which is like what I was doing with my fuzz pedal, where I don't need to know about all of the internals. I can just record data in and out and have a model of that, whether it's machine learning or not. I'm really interested in what they call the gray box models, where it's some of both. So yeah, there's a lot of different ways that people are using AI, but I think a friend of mine was talking about this recently, and he was like, the last 100 years notwithstanding, like through most of human history, the purpose of music for humans has been to make music, not to listen to music. So even if AI can make a lot of music, like that's not really the point for humans, it's to enjoy making it. So I think I mostly agree with
that. Can you hear me? I got a question for you. I've been a musician since I was 13, and for the last 10 or 20 years, I've used like digital performer in my computer and more and more plugins, but I also know C++ really well, but I don't know anything about circuits other than I know what a resistor and a capacitor is, and that's about it. But at the beginning, you showed that you could bring up one of your effects boxes, and then you could show the circuit. You could change this resistor to that value, and I wouldn't know how to do that or what it would do. But it would be interesting to have a user interface where you could tweak those kind of things with an English description of what you might be able to accomplish by changing the values of those resistors or capacitors.
Yeah, definitely. Yeah, so that's actually my friend Christian was working on a similar kind of problem using like a machine learning kind of system where, so he was doing it with equalizers. So a lot of times people will describe like, oh, I want my song to sound brighter or darker or full or something, which are all kind of nebulous descriptions. And so basically what he had done was kind of go through like having a bunch of people who are like expert listeners, like describe different types of songs and measure like the frequency response of those songs, and then tried to make an effect where basically you would say, okay, make this sound brighter, and it would generate the correct frequency response modifications to hopefully get you that relative to what the experts believe that means. Of course, different experts believe different things, so it's a little bit, it's never perfect. But yeah, I mean, that's a really cool idea, to be able to say like, oh, I want my distortion to sound, heavier, like more like a metal song, or, more like a Jackson Browne song or something. I don't know.
Yeah, or I want my Strat to sound more like a Telecaster.
Yeah.
So have they figured out why a Stradivarius sounds like a Stradivarius? Yeah, because I've seen article after article where they can't quite seem to figure it out.
Yeah, so there's a lab in Montreal at McGill that I know was doing some research on this a few years ago, where they got a normal Yamaha or mass-produced violin Stradivarius and put them in their lab, and mostly what you do is you tap it with a force hammer, and you measure like the resonant modes and the different face plates of the violin. And yeah, I mean, I don't know. It's it's always a little bit kind of like, what do certain people prefer, I guess. But generally with those types of acoustic instruments, it's mainly about kind of, you know, the luthier, the person who creates it, will sort of carve out that piece of wood, or maybe you do it at a factory with something that's more advanced than carving, but then you'll kind of tap it and listen to it and try to sort of take off material in certain places to make it resonate a certain way. And that's, I don't know, that's a very challenging thing. And so it's something that generally is kind of passed down from instrument maker to instrument maker, their own methods for doing that. Does a Stradivarius sound better than a Yamaha? I mean, probably. I don't know. I don't know enough about violins to know, but that's generally like how they look at these types of things. And you know, as with the Klon Centaur, I'm sure there's some amount of mythos around it too. The thing that I find really interesting that isn't always captured by these ways of studying things is that a lot of times the instrument that you're playing or the effect that you're playing with changes the way you play. So when I started playing guitar just a few years ago, something that I noticed a lot was that the way I play when I'm playing through a distortion pedal is very different than the way I play when I'm not. And so, you know, if all I do is take some pre-recorded signal and play it normally, play it through a pedal and say, well, which one sounds better? That's not always the best way to judge things, because really, if I'm the person playing and I'm playing through the pedal, I'm going to hear it in real time and adjust the way that I'm playing to. It's a merger of what I'm trying to play. It's sounding. So, I don't know. That's kind of my opinion on that sort of thing.
Yeah, that can be a problem when you're recording, because a lot of times you want to add effects after the fact, even an amplifier emulator, but that does affect the way you play. But still, it's convenient to say, you know, to tweak your effects and after the fact.
Definitely, yeah. Yeah, and that's one of the great things about plugins compared to hardware gear, is that with hardware gear, once you track through it and you record it, it's set in stone. Whereas with plugins, you can record through it and then after the fact go in and tweak it more. Yeah,
So
a lot easier
who do
for-
you think makes the best plugins?
Ooh, that's a good question. Well, there's different types of plugins. So for guitar plugins, there's a company called Nodal DSP that makes really good ones. I like theirs quite a bit. For circuit modeling in general, there's a company called Cytomic that is really, really good.
Sorry, what were those names again?
Oh, sure. Here, I'll. So, oh, okay. Yeah. Oh. Okay, I think Teams crashed. That's okay. So one is called Neural DSP. So like neural, like your brain, and then DSP for digital signal processing. They make great guitar plugins that are, I think, mostly machine learning based. For circuit modeling, like I was showing, there's a company called Cytomic, Cytomic. I think they're Australian. That's really, really good. I hope to be as good as that guy someday. And then actually for reverb plugins, in my opinion, the best reverb plugins in the world are made by a company called Valhalla DSP. And that guy is from Seattle. I've been trying to get him to come to a meeting, but I don't know. Maybe he'll come sometime.
Are your plugins available?
Yes, yeah. I can email folks with the link or something. All of my plugins are free, actually, so if you want to.
Oh,
Perfect. Yeah. Yeah, so mainly all my plugins are free because I don't want to do marketing, and then I work for other people who want to make their own plugins, and they sell them and then they pay me. So that's nice. Yeah.
I'm also curious about something, and no one's ever been able to answer it. When I was a boy, I played trumpet. And because I love the sound of a trumpet, and pretty much all I learned was how hard it was to play a trumpet, and I will never be a decent trumpet player. So I abandoned it. But I've been listening to synthetic trumpets for decades, and I can instantly tell they're a fake trumpet, they're not a real trumpet. Why is there no progress in being able to reproduce the richness and the beauty of a sound of a trumpet?
Well, first I would say, are you sure that every real trumpet that you've heard is real? Yeah, definitely. So there's kind of a couple challenges. So one is just modeling the sound, right? Getting something that can have the same timbre as the physical trumpet, which is a difficult problem, kind of a similar physical modeling problem like with circuits, but in the acoustic domain instead of electronic. The other problem that I don't think as much progress has been made on is the kind of performance interface. So if you're playing a synthetic trumpet, usually you're playing like a keyboard, which is very different from playing like with your mouth and like the expressiveness that you're able to achieve by like I mean I play saxophone too, and I have a similar feeling with like synthetic saxophones where it's like, oh, like the way I do pitch bends and the way I do vibrato and things like that aren't really captured by the kinds of uh, input that I would get just by playing on a keyboard and having, you know, a pitch bend wheel and a modulation wheel. Um, so yeah, there's a great conference called NIME, New Interfaces for Musical Expression, I think, where people come up with weird and different ways to control musical instruments with various body parts or other things. Yeah, and there's always really cool things that come out. But yeah, I feel like that's something where not as much progress has been made in terms of like, how do we come up with more expressive interfaces for interacting with digital uh, digital instruments. Uh, yeah, it's definitely a challenge right now. Um, I think the other thing too, for me at least, is that like sometimes that's kind of a choice too for like the music maker. Like I could use my real saxophone or I could use a synthetic saxophone depending on what kind of sound I'm trying to go for at a given time. Um, but I don't know. No, sometimes more choices isn't always good. Yeah.
Yes. Is there any interest in applying like computing accelerators, like neural networks, like with all the AI stuff you mentioned, or applying graphics cards to try and accelerate some of these computations?
Yeah, so that's definitely been a research area over the last 5 or 8 years or so. And my friend Travis is actually doing exactly what you've been saying, where he works on doing these very advanced symbol models. Symbols are very hard to model because you've got a ton of different resonant frequencies that are all kind of resonating at the same time. And so the way that he models them is very parallelizable. So he's been using GPUs for a lot of that synthesis algorithm. His goal is to kind of make like a full drum machine that's all running on his GPU and he can play it and so on. But generally, the problem that you run into with doing that kind of thing. So, for example, if I'm running all my plugins on my computer, and I have one plugin that wants to use the GPU or something, basically I have this kind of I/O problem where I need to get information from my CPU to my GPU and then back. And given kind of what I was saying about like the real-time deadline, that can sometimes be a challenge to interface with external hardware in general. That said, people seem to be doing it these days. I don't fully understand how, but so Travis has a bunch of papers that are published where he kind of goes through his process for doing it. And then there's a company called GPU Audio that's been around for a few years now. might just be marketing hype. I don't know, but they seem to have solved some of it. So yeah, it's definitely something that people are working on. But actually, what I've been doing for myself with neural networks is just trying to see how fast I can get them to run on the CPU. And generally, I found that you can get pretty far. You can't do anything like, large language model or anything. You can't get that to run in real time, but, a small recurrent network or convolutional networks. Um, but yeah, you definitely have a size limit. Out of luck until you can get your GPU running. Yeah. Everyone want to go home and make some music now? Sure. Yeah.
So how much do you have to worry about the operating system stopping your plugin and thinking it has more important things to be doing?
I actually had a few slides on like kind of the real-time constraints of audio programming. And in some sense, like unless you're on a real-time operating system, which like 99% of audio programmers aren't, you just have to hope that the operating system doesn't screw you over. I mean, I don't know. I feel like most people who are like running a studio or performing live or something are going to shut down everything on their computer as much as possible. But I don't know. If Windows wants to update, then maybe it causes some glitches in my plugin and there's nothing I can do about it. So yeah, I mean, we try to be very conscious of the things that we do have control over, like, memory allocation, not locking threads, things like that. Or not locking the real-time thread. But there's always a chance that something outside of your control will mess you up. Yeah, that's just something we live with. But for the most part, at least with, maybe since 2012 or so, I feel like operating systems are pretty good about not interrupting the audio process unless like they're about to crash or something, in which case your computer's going to crash, it's going to crash, whatever. Yeah, I haven't learned Freebird yet. Yeah, I haven't learned Freebird yet, but I'll have to learn it. Yeah.